Akash Rajesh es candidato a doctor por parte del Centro para la Ciencia de Datos de la Universidad de Nueva York, asesorado por el doctor Carlos Fernández Granda y el doctor Narges Razabian. Tiene licenciatura en Ingeniería Química, maestría en Administración de Empresas y maestría en Ciencia de Datos. Su investigación se centra en la construcción de modelos de aprendizaje profundo para aplicaciones de salud, con un énfasis particular en cambios de dominio, aprendizaje en datos no etiquetados y modelos interpretables que son cruciales en salud. Su tema de investigación consiste en utilizar aprendizaje profundo y aprendizaje automático para mejorar los resultados en medicina, incluyendo el pronóstico, diagnóstico y rehabilitación. We are ready to listen to your conference using deep learning methods for healthcare applications, a case study in quantifying stroke rehabilitation.
Thank you for the kind introduction. Hello everyone, my name is Akash and I'm in my current final year of my PhD doctorate studies at NYU and advised by Dr. Carlos Fernandez Granda and Dr. Nargis Razavia. So today I will be primarily talking about my research that I have done during my doctorate studies. And that would be on stroke rehabilitation and using deep learning methods to improve the outcomes of rehabilitation. So I'll be sharing a slide and I would encourage anybody, if they have any questions, they can stop me anytime and I will be happy to answer any questions. So let me share my slides and let me know if you can view it. Can you see the slides?
Yes.
Okay. So basically what I will be talking about is harnessing data and deep learning methods for improving stroke rehabilitation in stroke patients. So this would be the primary agenda of the entire talk. Like I will be first describing the stroke rehab dataset, like what the stroke rehab is, what's the task that we are trying to accomplish, and then some methods that are some deep learning methods that we have done, that we have experimented with, and what results we have achieved, and then how we went about improving those. So that would be covered in the third section, which is segmentation and sequence models. And then finally, we end with our presentation with one more project, which is related to the stroke rehab, where we want to do a data-driven impairment quantification, like how we can use data to determine how impaired a patient is. Like, is he severely impaired or mildly impaired or just almost healthy? So something like that. So let me start with the first, with the stroke rehab dataset. So here we have worked closely with our colleagues from the medical school, and they were the primary people who were responsible for who contributed a lot in collecting this dataset, because this dataset required to recruit a lot of patients, and then after recruiting them, they had to undergo some lab rehabilitation setting, and then they went ahead, collected the data, and labeled them. So they are like Avinash and Heidi are the main drivers, and then the rest of the team in the lab, they had collected the data set. So the entire credit goes to them. So stroke, so let's start with the basics. Like stroke, we know that stroke causes some damage in the brain, and because of that, that particular part of the brain which was controlling our motions, like for example the motor movements, the hand movements, that gets affected, and because of that there is some physical disability, and it's a leading cause of physical disability in US, with more than 1 million patients every year are getting affected by this. So after stroke, what happens? So after the person undergoes a stroke, there is some recovery that happens because the other parts of the brain can relearn that function. For example, let's say one part of the brain which was controlling my right arm is affected. So then the other parts of the brain which are not affected, they will try to relearn the function. So there will be some spontaneous recovery, but that recovery is not complete. It won't reach the pre-stroke level function that the person had. So to get a complete recovery, rehab training is required. So what this rehab training involves? So we'll see that. So this rehab training involves practicing like activities of daily living. For example, um, drinking from a glass of water, or eating, or brushing teeth, or combing hair. So those kind of activities they are told to perform. So those are called activities. Those are like at macro level. But then we can break down those activities into sub activities, like which are called functional movements here. Like for example, if I want to prepare a meal, so meal preparation is an activity, but then functional movements can be cutting vegetables, tasting sauce, stirring pot, and so on. And then that can be further broken down into functional primitives, which are called reach, reposition, transport, stabilize, and idle. So the idea is, if we do repeatedly, if we do these functional primitives a lot, there is a chance that there is a high correlation of recovery, and the person can regain the entire like what they were able to do before the stroke. That kind of movement ability they can regain. So what are these functional primitives? So let's I'll show you some examples, and it will be easier to grasp like that. So here is a reach. So th this lady is doing a reach with her left hand. So it's reaching the faucet. So that is the reach, just that much. Like reaching for something, like you reach for a glass of water. So you reach for a at a faucet in this case. Okay, again, we will focus only on this hand because this the label that transport is only for the left hand. So the transport is this. Like this person took the butter and then transported. Sorry, took the butter and then transported back to the table. So that's called transport. What is reposition? Reposition is after transporting the butter back, the person took back the hand and repositioned it in the initial position where it was. So after leaving the butter there, it came back to the original position. So that's called reposition. What is stabilize? So stabilize is like, again, we focus only on the left hand. This hand is stabilizing the butter so that the other hand can do a lot of stuff with it. So it's stabilizing as in holding on to something. For example, when we eat a meat, there is one fork which holds on to the meat, and then there is a knife that goes and does other motion. So this hand is actually doing stabilize. It's stabilizing the object. And lastly, it's idle. As the name suggests, it's just not doing anything. It's just idle, just there. It's not functioning. So these are the functional primitives, and the idea is to do these repeatedly more and more. And if we do more, the recovery happens, and the patient can recover to the original uh, ability of moving around. Okay. So what is the optimal dose of doing this? Like how many times should the patient do this? That's the question. So people have done some studies, and in animals, it is said that they require around 200 to 1,000 times of repetitions per day to have any recovery. So they did this with mouse, where they were given um, some things, and they were told to move around, and with the help of they were able to see that how many times they did those actions, and they saw their improvement over time. But for humans, we don't know that, because in humans, we have not systematically quantified how many times this dose are given. Some studies suggest that we might be underdosing our patient by 10x. So that's why it's important to develop a tool that can help us quantify the dose. Now, there are different ways people are using to quantify the dose. One way is to see what's the time in the therapy. For example, they are doing the therapy for half an hour. They are doing the therapy for 1 hour. So just like the time in the therapy. So people generally use that to quantify the dose. Or they can hand tally. For example, how do they hand tally? So they capture a video of the person doing those actions, and then they go back to the video and then slow it down and then see each action and count manually. Or they can be motion capture systems. For example, you have videos around, and then that videos will be able to capture the motion, but that can be affected by the occlusion or by the surroundings may change, and that may cause an issue. Or it can be done with the activity monitors, but the activity monitors are not that high grain, like they are not high resolution, so it cannot capture these subtle motion. We saw that it's very quick. These things happen very quickly in our case also. It's less than a second long. So we need something more than that. So another study again shows that in out of the 215 cases, 215 studies, uh, approximately 20% does not do not record any dosing information. In 75%, the time in therapy is used. And in only 5% the repetitions of motions are actually trying to quantify that. So therefore these kind of physiotherapy sessions, they are not replicable, and to make it replicable and to get the exact number of doses the patient are doing, we need some kind of a tool, and that's the tool that we are trying to build here. So again, manual tallying, as I already said, that 1 minute of video takes 1 hour of manual labor to tally, to count these things, to label these things. So that's why they have, like the my collaborators in medical school, they have done this manual labor. They recruited a lot of students to label these videos. Like they showed them these videos, and they taught them how to label these things. And once they were able to do that, we gathered a lot of training data, where we have a lot of videos and then we have a lot of label data. So that's why now we can use machine learning to 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 take this challenge and to automate this task. So the idea is basically to automate, is to identify which perimeter is happening at what time, and so that we can then count the perimeters. So at the end of the day, we are interested in the count of perimeters. How many ideals the patient did, how many reaches the patient did, how many transports the patient did. That's what we are interested in. That's what the physiotherapist is interested in. So this is the data set that we created with 3,300 trials, which is one of the largest, with 50 odd stroke patients and 20 healthy subjects. So just to give this comparison with other data sets that are out there, other data sets generally in action recognition space, it's around 20 subjects or 25 subjects, but it's like this is a larger data set with 2x number of subjects or 3x number of subjects. And we have high quality labels where each data is labeled by three annotators, and there is a high inter-rater reliability between them. So that way we ensure that the quality of labels is high, and the time taken to label these is as I told, it's already time consuming effort. So around 2,700 hours, and total recorded training sessions are 44 hours. And additionally, it's a multimodal data. So we have video as well as IMU sensors. So the IMU sensors, here we see there are 9 sensors, which are 3 on the left hand, 3 on the right hand, and 3 on the back. So they capture a lot of signals like acceleration, gyroscopic reading, and joint angles and whatnot. So quaternions. So all those things are captured by IMU sensors, and then we have video. And just to give a comparison of this data set with other data sets that are out there in the open source. So our data set has around 120,000 annotated actions, whereas the other best data set that we have is around 32,000 annotated actions. So in a way, it is almost 4 times as large in terms of the number of annotated actions. And another interesting aspect of the dataset is we have different cohorts, as in we have a mild and moderate cohort where the patients are mild and moderately impaired. We have divided into 2 sets, training set and a test set. And then we have severely impaired patient. This is like a challenging test set. And then we have healthy cohort where we have healthy patients. An interesting thing is in this, all the subjects are semi-impaired. What I mean by semi-impaired is they are either one hand is only impaired, either the right hand or the left hand is impaired. Both hands are not impaired. So to get these kind of patients is very difficult. So where only one, because this study is mainly focusing on semi-impaired patients where only one arm is impaired, either the left arm or the right arm. So that's the distribution of left versus right for the entire data set. And another thing that you see here is the Frigo-Meyer assessment score. So that's the score that determines how severely impaired the patient is. And this score goes from 0 to 66, where 0 implies severely impaired and 66 implies healthy. So they do some assessment based on, there is a assessment that physiotherapist carries out, which determines the impairment of the patient. Okay. And here is one example of how the data is being captured, where the video is captured, and along with this, all the different sensors like orientation angles, accelerations, anatomic angles, everything is captured at the same time. So it's a synchronous data set that we are capturing, right? Here the person is doing the activity of drinking from a glass of water. So the contributions of this data set is the first benchmark data set for short duration action. So as we saw, this actions that we are doing in this data set are very short, like reach, transport. They happen in a matter of seconds, like even half a second or 1 second maximum. And they contain multiple modalities. They have realistic distributional shift, like we have healthy subjects versus stroke patients. So we can actually use models to determine how generalizable the models are when we train on one cohort and then test it on other cohort. And then it's a clinical benchmark data set because it's a real world data set here. It's not a fabricated data set. So it can help in clinical, when we train good models on that can translate into meaningful applications in the real world. So now we go into the modeling aspect. So we have decided we have done the data set. First section is done. The second section is modeling aspect, where we start with the classification for identifying primitives. So idea is we have a lot of data, which is the time series data that is we are capturing from the IMU sensors. So first we'll focus only on the IMU sensors and not on the videos. And then what we do is we get the 2-second window of all these are all the sensor readings. They are very noisy, high dimensional readings. And then the red one is the labels. Like for the first this many seconds, they are doing idle. And then there is a reposition that they do. Then again, they do idle for some time. And then they do reach for some time, and so on and so forth. So the bold red line is the label. So what we try to do is we try to get a 2-second window and try to predict what's happening at the center of the window, like what primitive the person is performing at the center of the window. And now we can use this model, and for every 2-second window, we can keep getting the center label, and then we can move this 2-second window to get the entire sequence of labels. So that's the idea. So what we did in this study was we compared our model with the traditional models that are out there, like random forest, or fully connected neural network, or LSTM, or a CNN, or a ResNet, or LSTM. And we did some modification of the CNN, and we found that to be working the best. That modification was we had an embedding module that embeds all the different sensors in one space, and then we have something called instance normalization. Yeah, we are not going to detail of what those modifications were, because the idea of the presentation is to see how we improve upon this. So this leads to some balance accuracy of 69%. So that's good enough. And this is that model in action. So here we see, here is a prediction, here is a ground truth, and it's only for this arm because this arm is an impaired arm. So I'll play this video. You can see that I have slowed down the video so that it can be easily seen. So here it reaches and then stabilizes it, then transports back. So here it's doing an incorrect prediction, but now it's correct. In most of the cases, it gets the correct ground truth. Then it again stabilizes. And reposition back to the, okay. So this is the entire, like this is the model that we built, and it seems to be working good enough. There are some errors, but most of the time it's capturing the ground truth correctly. But now we move on to the next section, which is segmentation and sequence to sequence. So there we want to see how good is it for counting parameters, because at the end of the day, the patient, the physiotherapist wants the counts of the parameters and not like how good the accuracy is, because they don't care about the accuracy as such. They want the counts to be correct. So we need to have correct metrics to evaluate the model in order to get that. And what are the correct metrics? So one, we can use two metrics here, the true positive rate and false discovery rate. So true positive rate is a fractional of ground truth parameters that were correctly predicted. And false discovery rate is a fraction of predicted parameters that was spurious. So what is the true positive rate? Is, let's say we have 10 ground truth parameters, in which, like, that's a two are reaches, two are transports, five are stabilizers, and one is an ideal. So out of that 10, let's say we are able to predict 8 of them correctly. So then the true positive rate would be 80%. And if the model incorrectly predicts some primitives, like for example, it says that there are uh, 3 ideals instead of 1 ideal. So then it's incorrectly predicting 2 primitives. So then those 2 primitives will be counted as false discovery rate. So ideally, we want the true positive rate to be as high as possible and false discovery rate to be as low as possible. So now we can't keep a track of 2 metrics. So we combine them to be in one metric, which is an F1 score, which is just the harmonic mean of the two. Harmonic mean of 2 positive rate and 1 minus the false discovery rate. So that's the F1 score. Another way of looking at this is from a speech recognition. So we took the inspiration from speech recognition literature. So in speech recognition, what is happening is we have a sequence of audio like signals, and that sequence has to be converted into words. So that's the task of speech recognition. So the input is a time series of some audio signal, and the output is a sequence of words. In our case, it can be very similarly correlated, or as input is the sequence of, or the time series of IMU sensor data, and the output is a sequence of primitives, or the sequence of words or primitives that we want to predict. So one way they evaluate the model is using character error rate. So what is so here instead of character error rate or word error rate, we can use action error rate. So what is action error rates? Let's say prediction of the model is reach, ideal, and transport, whereas the ground truth was reach, transport, and reposition. So action error rate basically calculates how much edit or how much change we have to do in the model prediction so that it matches the ground truth. So for example, in this case, we don't have to do any change because reach is matching reach. Here, the ideal doesn't match an ideal. So we have to delete this ideal. So that's the deletion, one deletion. This transport doesn't meet because there was no transport here. So we have to insert a transport. And then we have a then we have a reposition, which was instead predicted as transport. So we have to substitute that. So we have to do 3 changes in this entire ground truth sequence in the model prediction to make it a ground truth, to match it to the ground truth sequence. So this addition would be 3. The numerator would be 3. The denominator would be 3 because the total number of ground truth sequences, total number of ground truth primitives are 1 reach, 2 transport, and 3 reposition. So 3. So the AER for this would be 1. The idea is the AER should be as low as possible, which should be almost to 0, so that the model doesn't have to do any changes. We don't have to do any changes to the model prediction so that it matches the ground truth. That's the idea. And again, we can actually calculate the FDR and TPR also using these deletions and substitutions. So the other metric that we just discussed can also be calculated using the same logic. So let's see how the model that we have. The proposed model is the model that was the CNN model with almost 70% accuracy, balance accuracy. So the AER for that is 41.41. And the RF model that we had, so that was 0.54. So we definitely improve from the non-DL methods if we use deep learning. But let's see how we can improve further. So we have to reformulate the task. So earlier what we were trying to do is we're trying to predict the center time step. But rather than that, we can actually segment the entire time series. So by segmentation, what I mean is this entire time series, in this chunk we are doing idle, in this chunk we are doing reach, and in this chunk we are doing transport. So this is called the segmentation. So we are segmenting the time series into different chunks of primitives. So there are standard methods in action recognition literature that helps us to do this segmentation task. So the models that they generally use is MSTCN. And just by changing the model and the reformulating the task, we can improve the AER. Once the AER is improved, we can improve further on the AER by just changing the early stopping criteria. So here the early stopping criteria was frame accuracy, but it can be changed to AER that is of our concern rather than frame accuracy, and then we can improve upon the action error rate. And finally, we can always apply the smoothing window to further smoothen the output, and then we can get a better AER. So we can see, like, just by changing the model architecture and the way we formulate the problem, we can improve the AER from 0.41 to 0.31, like almost a 25% improvement in the metric. But one thing, there is an issue with the segmentation model is our data set has, as I told already, that we have a lot of shorter duration actions. For example, we have a lot of actions which are less than 1 second, whereas the other data sets on which this model was designed, they had a lot of longer duration actions. What we found is when the duration of the action is longer, it's much more easier to identify the boundaries between the two primitives, between the two actions. We have to identify the boundaries to make a good segmentation model. So if the duration of the action is longer, the accuracy of finding the boundary is much higher. But if the action duration is shorter, the boundary detection is accuracy is much lower. The understanding is like when the action is very quick, the boundary between the two actions is very blurred. So we cannot say where actually the action is happening. So that's why the boundary detection accuracy is low. So in that case, what we suggest is we use a sequence to sequence model where the input is a sequence of primitives, as we saw, and output is, instead of frame-wise labels, we can actually give just labels for the primitives, like for example, reach, then transport, then ideal, and then end. So like that's the end of the sequence. So it's again inspiring ourselves from the speech recognition. In speech recognition, they don't say that, okay, this particular time was the word this particular time the word the was present. They just predict the word itself rather than doing a frame-wise prediction, like time-wise prediction. So that's what we are trying to do here. And if we just do that, we improve upon the accuracy even further, or we improve upon the AER metric even further to 0.305. So we are able to correctly formulate the task and use a correct deep learning model. We can actually improve the metric that is of concern. And we can also, and finally, we want the count. So here is the count accuracy. So there are different activities in our data set. And for every activity, we see that the count accuracy, in most of the cases, it's less than 10%, but in some cases, it's higher than 10% too. So obviously, there is some more work to do. But we see that the counts are getting closer to the ground truth counts. So that's what matters for the physiotherapist at the end of the day. Another study that we did in this stroke rehab is to see the generalization across cohorts. So like if we train on healthy subjects, how well it does on the stroke patients or on the healthy subjects or on the severely impaired subjects. So if we train the model only on the healthy subjects, it does well on the healthy subjects, but it's not doing that well on the stroke subjects. Just to remind, the best performance that we were getting was 0.305. 5. So this is, the lower is better. So this is bad. And here again, severely impaired, we are not able to perform well. Next is stroke patients. We only train on the stroke patients, and interestingly, that improves the performance on the stroke patients, but the performance on the healthy patients is not degraded. The understanding here is some stroke patients which are mildly impaired, they perform as similar to healthy subjects. And that's why we can use those mild subjects to emulate healthy subjects. And that's why the healthy performance is also intact. And severely impaired performance also improves a lot. And if we combine on both the healthy subjects plus stroke subjects, stroke patients, we improve it even further for stroke patients and healthy subjects, and for severely impaired as well. But again, we saw that severely impaired is much higher still than what stroke patients are. So here is a challenge. This is a challenging data set, and it's an open question of how to improve the model further on the severely impaired patients. Because severely impaired patients move in a very different way than the other two cohorts, like the mild and moderate cohort. We did the same procedure for the videos. So the entire thing that I talked about till now was for IMU sensors, but we did the same procedure for videos, where we first take a 3D model to get like a feature extractor, and use this 3D model to extract features for each frame. We actually use the penultimate layer features to extract the features, and these features are 1D vectors with 432 dimensions. Once each frame is represented as this 1D vector, we can actually use the same methods that we just saw in the IMU sensors. And we see the similar results happening. Like for MSTCN, the number is high, but if we keep on doing and go to sequence to sequence, we can improve upon and the improvement is much higher. From 0.39, we can actually go down to 0.32. Something that we were looking further into is like we calculate the confusion matrix of how the video data is performing, and the model that confuses a lot between ideal and reach, and ideal and stabilize. And for IMU sensors, it's mostly between stabilize and reach and transport. So between reach and transport, the only difference is the grabbing, like the grasping information. Because if I am reaching for something, it looks almost like I am transporting something. The only thing is I don't have anything in my hand. So grasping information is very important. So we thought that if we combine these two modalities, we should be able to overcome these errors. So we went ahead and combined them, but we found that we combined in two manners. One is early fusion and one is late fusion. I'm not going into detail in what these early fusion and late fusion methods are, but we found that the model was not able to improve upon the single modality numbers. So there's something we have to do for the future work of how to successfully combine these two modalities so that we get benefits from both the modality correctly. So the future work involves doing some contrast shift pre-training between these two modalities, and then fine-tuning it, doing a combined fine-tuning on that. Another way is, as I said, that grasping information can be important. So we can actually use open pose kind of a model to get the grasping information and then combine it with the IMU sensors to improve the IMU performance. So that we can do like a hybrid model approach. And finally, we want to move from lab setting to home setting, so that even in homes, when the person goes home, at home, we can actually monitor his movements, and we can monitor how well the person is moving around and how well he is improving, or he or she is improving. So that brings me to the end to my last section. The last section is data-driven impairment quantification. So now we saw that the data was divided into cohorts. Like there was some severely impaired, there was some mildly impaired, and there were some moderately impaired patients. So the idea is, how do we get this impairment measurement? So we saw that we have some FMS score or FMA assessment that we do. Because of that, which goes from 0 to 66, which can help us determine, okay, how impaired that is. So how do they calculate that score? That score is calculated using a trained, there's a person who goes and who sees if they are told, the patient is told to do some action, If they can perform the action, they give 2 points to it. They are not able to or partially able to perform the action, they get 1 point for it. And if they cannot perform, they get 0 points for it. And then they sum up all the scores, and that's the FM score that we saw. This is a video that basically explains how, like, an example of that. I'm not going to play the entire video, but I'm just showing you how it is done.
With the patient seated edge of the table, begin the assessment by assessing the biceps and triceps deep tendon reflexes.
I'm not sure if the audio is clear, but basically what the person is trying to do is this person is an assessor. He's trying to assess this patient, and they are told to do some actions, and he does some tests on that patient, and they can basically determine how well the person can move, and that is the way they determine the severity or impairment level. The understanding is we want to move away from this and make it more data driven. So basically, can we get the impairment scores from the data itself and not based on some subjective, because it's a time consuming one. It's time consuming because we have the assessment has to be done by a person, and they have to go for this assessment, and it's expensive, and it's subjective to the person. Like, this assessor can say that this person has a score of 45, but some other assessor may say that this person has a score of 30. So it's a subjective decision, right? So what we want to do is we want to do it data driven. So one naive approach of doing a data driven way is gather a lot of training set of impaired patients, gather a lot of scores for their impairment, and train our supervised model. But the problem here is to gather so many patients' data. As we saw, these patients are semi-paretics. Semi-paretic means they have only one arm impaired. So it's very difficult to get these kind of patients, and it's very expensive too. We have to recruit them. We have to give them money so that they come into the rehab lab and do the actions. So that's why it's difficult to acquire these data sets. So can we use some other data to do this? So there is one way that we propose in this, and the way is to identify how normal people act or how normal people move, and then use the stroke patients' data to understand how do they deviate from normal. The higher the deviation from normal, the higher the impairment it would be. To concretely describe our method is basically named COBRA, which is confidence-based characterization of anomalies. So what we do in this is, step one, we gather a lot of healthy subject data. This is very easy to gather because we don't have to go around to find a very specific kind of impairment. So we can gather we can recruit some graduate students or some elderly people as well to get a demographic variation, and then we can tell them to do some action. Once we gather the data, we label the data as well with the primitives that we have. And we train a model. The model is exactly the same model that we saw in the first section. The model is trying to predict which primitive is happening at what time. So that's the clinically meaningful task that the model should do. Once we have this trained model, we can have the stroke patient's data, and we just do an inference on this stroke patient data using this model. The model that is trained, we use this model here itself, and we do an inference. And based on the inference, if the person is as good as healthy, the score of the confidence score will be high, and the impairment level would be low. If the person is severely impaired, the impairment score would be the confidence score would be low because they are very different from the healthy people, and they would be severely impaired. So that's the idea. Idea is to see the confidence level score and using that as a proxy for impairment. So here we only focus on one activity. The activity is to move this particular object on the circular table. Since this activity is a standard activity, it helps us to narrow the confidence to be only related to the motion of the patient, because confidence can also drop if the model sees some other data from an healthy patient. For example, the data was trained on people moving this object on the circular table, And the inference data is the person is doing an action of drinking water from a glass. So in that case also the confidence can drop, but that drop in confidence is not correlated with the movement ability. We want the drop in the confidence to be strictly correlated to movement ability, so that that's a correct we find the correct correlation of that. So that's why we just restrict the actions to this standard task, where healthy person does this task and the impaired person also does the same task, exact same task. So here I am showing that how the model performs on the healthy subject, and since they are able to perform well on the healthy subject, we can assume for safely that it understands how the healthy people performs the task. Once we know that the healthy model is prepared, we can actually give the model some data from the impaired patient, and we see that there is a shift. So here is a patient who is a healthy patient, who is a healthy subject, and that was not in the training set. And we see that the score is high, and for an impaired subject, the score is low. An interesting thing is this is not a novel concept. This is already done in the out of distribution detection literature, but they do it on the instance level. They do it for each example separately. We suggest that we do it on the aggregate level. Like for example, there is multiple instances from a one patient, and we get kind of an aggregate, like a mean or standard deviation, and we then see the difference between the two distributions. That way, it's much more robust, because in instance level we can see that there can be overlap, and it can be more noisy. So that's why we suggest to do it in the aggregate level. And here is an aggregated by the subject. We see that this is the healthy subject, and they are more concentrated in 0.9, like it's higher probability, higher confidence. Whereas as we go from healthy to impaired to severely impaired, the confidence keeps on dropping. And we also should do it on the individual level basis. So we have the correlation between the FM score that we have. That's a ground truth, and in a way, and we try to correlate our score, the confidence score that we calculate, and we see that the correlation is quite high, with which is statistically significant, with p-values less than 0.0001. So that's and then finally we go and we'll try to see how this confidence score, by what features that in our IMU data, which is affecting the confidence score. So here the red ones means the sensors that are attached on the impaired arm. We have to recollect that only one arm is impaired, the other arm is not impaired. So the red are the sensors that are attached on the impaired arms. The green are the sensors that are attached on the non-impaired arm, and the blue ones are the sensors that are attached on the three sensors on the back of the patient. So we see that the highest contribution is from the impaired arm, which is understandable. So this means that the model is looking at the right arm to get the model confidences. The other interesting thing that we see is it's not giving much importance to the back of the patient, because the back is not moving much in the healthy patient. They don't play a much important role in the confidence score. So for example, here this patient is more impaired. So rather than moving only the arm, he's also moving his back a lot, so that to compensate for his limited motion of the arm. So that is what generally the people or the physiotherapist looks at when they are determining the impairment level. But the model is not looking at that. Model is not looking at how they are moving their back and forth. They are looking more on how they are moving their arm, and how does that compare to the healthy patient. So that is what the model is looking at to determine the impairment level. And this is a general method that can be extended to other activities as well. So here we only did for one activity, which is like that round tabletop activity, where we have to put things in this round pattern. But it can be done for other activities like brushing, drinking, combing, and so on, and also for the videos. An interesting part in the video is we have to be cautious about the confounding factors. So what is a confounding factor? So here there is an object, but you cannot see it. So the object is camouflaged with the background, but here you can see an object. So there was a drop in confidence just because the object was not visible from the background. So this is not related to the movement ability confidence drop. So we have to make sure that such confounding factors are not there in our data set, because this data set, the drop in the confidence may not be correlated that highly with the movement ability. So we have to make sure that this doesn't happen. So in future work, basically we provided the saliency maps where we can see which sensor is causing the drop in the confidence. So we can actually target those abnormalities and perform some physiotherapy to do some targeted rehabilitation. And second one is we only saw the correlation of the confidence score with the FMS score, but we did not see how the confidence score changes if the person improves. So you have to see how responsive this confidence score is and how reliable this confidence score is to the clinical change in the patient. So we have to do some long-term study to make sure that this confidence score is the correct metric for evaluating the impairment of the patient. So that's the end of my presentation. Now I will open it up for any questions. I can go back and forth. So let me know if there are any questions. Here are the full papers that I summarized today in my presentation. If you have any other questions regarding that, you can read these papers. Yeah, and these are the acknowledgements who helped me in my project from data science and from Mobilis. Like this is the medical team and this is the data science team. That's it.
Thank you very much for that interesting topic. Does anyone have a questions? Students at Paraninfo, questions? Okay, I'm getting questions from the chat. I'm going to read the questions.
Okay.
What is the most difficult part of labeling and what possibilities exist of improving this task?
Yeah, so the most, I'll go back to that slide. So the most the challenging task of labeling is to slow it down. The video, it takes a lot of time to label manually. So let me just go back, sorry. Yeah. So what they have to do is they have to actually slow it down by almost 2x or 3x to able to see this motion happening, because this motion can happen. Like, let's say, see it from your point of view. If you are to reach for a glass, how quickly you do it? You don't take even 1 second to do it. So yeah, they actually have to slow it down and then do the labeling. So 1 minute of video takes around 1 hour of their effort. So just 1 minute of video, they have to slow it down to so that they can exactly see where the motion started and where the motion ended, and that's how they label it. So that is why that's the most time consuming and an expensive part. And how can we improve that? So one way of improving, which is a good question, is we can use these models that we have trained right now to give some pseudo labels to the video, and then we can go ahead and the manual effort can be only to correct those labels. So most of the work is done by the model now that we have this trained model, and they have to only correct the data set, correct some wrong labels. So that way we can increase the speed of labeling and we can get more data collected.
Okay, thank you. Another question. One of the open discussion in machine learning algorithms is bias, sometimes inherent in the data or the population used for training. Does your work present any type of bias?
Yeah. So the bias, that's a very good question. Like there are so that's why we make sure that the demographic divide is it's divided in terms of, so I have not shown here the demographic like in terms of race divide, but we also have a diversity in terms of race. Like we have some Asians, some Black population, some Caucasian population, some Latin American population. So we have like a good spread of those patients. And again, in terms of impairment also, we have a good spread in the like we have healthy, we have severely impaired, we have moderately impaired. And in terms of gender as well, we have like equal genders. So we try like the collaborators in the medical school, they actively try to make sure that they have a representative population in the data set, and it's not biased towards one population or the other population.
Okay, thank you. Another question. According to your presentation, deep learning offers better results than other machine learning algorithms based on the lack of transparency in the way the algorithms work. Could it be reliable to make a decision based on it?
Can you please repeat the last part of the question, because I was not able to hear that.
Okay. I repeat all questions. According to your presentation, deep learning offers better results than other machine learning algorithms based on the lack of transparency in the way the algorithms works. Could it be reliable to make a decision based on it?
So just to understand, the questioner is asking, can these methods be reliable to take some actions on by the physiotherapist on these outputs? So that's why, like we saw in the end of the presentation, here we try to show which actual features are contributing how much, so that they have, so these results do align with what they were thinking. So basically this improves the confidence of the doctors in the model. So interpretability is very important in the deep learning for medicine, and this is one way of improving the interpretability, is to see which are the features that are contributing the most to the output, and making sense of the output, and seeing that if they align with their current knowledge of the medical medicine that they have. So here it did make sense, and that's why they were much more comfortable of using this model's output in their studies, or in their when they are recommending anything to the patient.
Okay. Does anyone have questions? No? We thank you with the virtual delivery of the certificate issued by the Universidad de La Cañada.
Which NGO?
Let me a second, please. Okay. A certificate of participation. This is present to Dr. Akash Rajesh Keiko for the presentation using deep learning methods for healthcare applications, a case study in quantifying stroke rehabilitation at the 4th International Conference on Artificial Intelligence, Data Science, and Applied Computing, Teotitlán de Flores Magón, Oaxaca, Mexico, on November 16th, 2023. Thanks so much. We hope to see